What's up, guys? This is the second video for Math 6 on 7.5, writing and graphing inequalities. And we hadn't gotten to the last problem, so we're going to do this, and then I'm going to do an introduction to the next section, and you should be ready to go. All right, how can we describe a real-world situation with an inequality? Got this sweet picture here. I imagine it's going to have something to do with something in space, and of course it does. The NASA Solar Probe Plus, which sounds pretty awesome. It sounds like also a new phone. Solar means sun, of course. Can withstand temperatures, I'm guessing up really high, up to and including 2,600 degrees Fahrenheit. Now, yesterday we talked about looking for words that will tell us that, there's an inequality here. Up to and including. Less than, or equal to, greater than, or equal to. Think about what those words might mean. Write and graph an inequality that represents the temperatures the probe can withstand. Okay, well, what don't we know? And, teachers always ask that question, but it's really a tough question. I mean, what is it that we don't know? And if you read this, the thing we don't know is what temperature the probe is actually dealing with at the moment. So we have to declare our variable. And declaring a variable is saying, okay, I'm going to make up a variable, and this time I'm going to call it t. I'm going to say what it represents. What does t represent? It represents the temperature, probe, whoa, it cannot do R's. Probe is experiencing. Of course, that's kind of weird. That's like almost saying like it can feel things. And of course, the probe is made of metal and circuitry. I'm sure it can't experience anything. But I think you know what I mean. It's what temperature the probe is at that current moment. Okay, well, T, now we have to write an inequality, because T can, think about this. It can be up to and including 2,600 degrees Fahrenheit. So can it be 5 degrees? Sure. Can it be 10 degrees? Sure. Can it be 1,000 degrees? Sure. In fact, it can be everything up to 2,600. So hopefully you guys are already thinking, well, T can be less than 2,600. The probe won't burn up into a crisp if it's less than 2,600. But it can't be greater than 2,600. It can be equal to 2,600, but it can't be greater than 2,600. And so this means all the values of T that the probe can be are less than 2,600 degrees or equal to 2,600 degrees. For students who want to really, really think about this, there actually is a lowest temperature. So you could make, later on we're going to talk about compound inequalities. I could make another inequality here, another less than, and T would be in between. But that's just for people to think about for later on, that the temperature is actually in between the lowest possible temperature, called absolute zero, and of course the highest temperature can withstand 2,600. Okay, the problem is with this sentence is it has lots and lots and lots and lots of solutions. Solutions are values that make the inequality or equation true. So I'm going to put 2,600 in the middle here, and then I'm going to number by maybe, I don't know, 200s. So this would be 2,800, this would be 3,000. There's a lot of ways that you could number this, but I'm just going to use this 200 for now, and we'll use the arrows to represent values that are any further. Okay, yesterday we discussed about open and closed dots. And the question we have to ask is 2,600 a solution to this inequality? If I substitute 2,600 in for the variable, the value of the variable that makes the inequality true, would 2,600 make this true? And the answer is yes, because 2,600 is not less than, but it's equal to, that line down at the bottom, 2,600. So we want a closed dot which says, yes, indeed, this is a solution. Now, what other numbers can T be? Can T be 3,000? Is that a solution? Can I substitute 3,000 in here? No. Is 3,000 less than or equal to 2,600? No, 3,000 is greater than 2,600. So 3,000 is not going to be a solution. How about 2,200? 2,200 is less than 2,600, so it is a solution. And this kind of tells you that all of the values that are to the left here, including the ones way down there, are included in the solution set. And for you smarties out there saying, yeah, but you said there's an absolute zero. Yes, this would only go to a limit, but we are just going to assume that that limit does exist and that this is just pointing in another direction of all the values that we care about. What was the first thing we did? We've declared what the variable represents. Oh, it doesn't do vertical movement very well. All right, take that into account. Write an inequality by identifying the blank blank in the problem. Write an inequality by identifying the blank blank in the problem. What words are we looking for? By identifying the clue words in the problem. And we did that. And sorry about this blue thing here. It's just saying that there's a space there. Clue words. What were the clue words? Up to and including. Up to and including. So those are the words we have to think about what they mean, and then we can start to write the inequality. By the way, the T is actually the NASA solar probe plus temperatures. So this is the variable in words over here. It's kind of right here, right? This temperatures is the variable, and it's relating to the actual solar probe. So here's the variable, less than and including or equal to 2,600. Check your graph by blank a value from your graph into your inequality. How did we do this? We were substituting these values into T to check if they made the equation true. And it looks like I left plenty of room to write substituting. You guys writing right now is like, this is really hard. You guys are probably already done and you're just watching me suffer. That's really awesome. Thanks, guys. Oh my gosh, you're so kind. Why? ¿Por qué no estás haciendo? All right, there we go. No, I don't want to select. Yeah, looks like a kindergartner writing. That's rad. Okay, so we finished these notes, but you guys know I like to go. I like to look at where we're headed, and where we're headed is into using the properties of inequality to solve inequalities. So just to give you this practice, why don't we try something like this? If I say x plus 3 equals 5, you guys have already learned how to solve that. And solving means we're going to find the solution. And we find the solution by finding the value of the variable that makes the equation true. Well, right now we don't know the value of the variable. We know that whatever the variable is, plus 3 equals 5. Yes, I know it's 2. I know it's 2. But we're going to use the properties of equality to prove that the solution is x equals 2. In fact, I'll just write x equals 2 just for those of you who are so excited. Oh my gosh, x equals 2. I know you know that. But more importantly, how do we prove that? Because that's what we're going to be doing later in algebra. So x plus 3 is equal to 5. We can do the same operation with the same number to both sides. We're going to use the inverse of addition, which is subtraction. We're going to subtract 3 from both sides. What's the purpose of that? Positive 3 and negative 3 are opposites, and so their sum is 0. 3 plus negative 3 is 0. What's the only thing left on the left side of the equal sign? It's just the x now. X is just by itself. This is essentially x plus 0. This is the 0. Okay, 5 minus 3 is 2. We've proved that x is 2. And of course we can prove that even more by taking the 2 and substituting it back in for the x, which is what you guys kind of already did in your heads. 2 plus 3 equals 5. And of course, that's true because 5 equals 5. Okay, now what about this? What about x plus 3 is greater than or equal to 5. I want to know all the values of x that if I add 3, I get a value that's greater than or equal to 5. Well, this is the cool thing. This is where we're headed. Using what we did here, what do you think you do here? If you said subtract 3 from both sides, you're right. Once again, these are opposites, so there's 0, so it leaves you just x. Now, I didn't put a line through the middle. I didn't want to make things too confusing, but I mean, I can do it. I could put the line there, or a dotted line, or a dashed line, or however it is that you want to do it. But I'm not going to do it this time. I think you guys can handle not doing it. This inequality, it's not an equality. This is an equality, or what we call an equation. This is an inequality because it's not equal to, the left side is greater than or equal to the right side. Just come straight down. 5 minus 3 is 2. Okay. Now, let's think about this. Is this true? This is saying x can be any number that's greater than or equal to 2. So I'm going to make a little graph of our solutions. I'm going to put a 2 here, and maybe a 3 here, and a 1 here. Is this a closed dot? Oh yeah, it's a closed dot. Remember, if there was no line underneath, there was no equal to or equal to, this would be an open dot. We went over that in yesterday's video. So if that wasn't there, this would just be an open dot, but the or equal to is there. So 2 is a solution. So 2 is greater than or equal to 2. Yes, 2 is equal to 2, so this is a solution. What about 3? Can I substitute 3 in? Yeah, because 3 is greater than 2. So that means I'm doing this in red, I realized. Everything's in red, but you guys can understand. All the values this way will make this equation true. Or inequality true, I should say. Whoops. Inequality true. Does that make sense? Because look, 1, is that greater than or equal to 2? No. 2, is that greater than or equal to 2? Yes. 2 here. 2 plus 3 is 5. Is 5 greater than or equal to 5? Yes. 3. If I substitute 3 in for x, is 3 plus 3 is 6. That's greater than or equal to 5? Yes. So it looks like we've done it. Now, before, these were we were doing solving equations. We were using the subtraction property of equality. Guess what this is going to be called in tomorrow's lesson? The subtraction property of inequality. That's right. All right, you guys, thank you so much for watching the video, and please, you can go on to Big Ideas if you'd like to try the assignment. As always, I miss having you guys in class, but thank you for doing this. You're doing a great job. I'll talk to you later.